Hello everyone, I'm Chris McIntosh. I help teach the statistics courses, and I wanted to go over some of the correlation information in the Navarro text. This is from chapter 12 of the Navarro text, Correlation and Linear Regression, the first two sections. Correlation allows you to quantify the relationship and direction. Correlation allows you to quantify the strength and direction of a relationship. You need two continuous variables, and you're answering the question, what is the direction strength of the relationship between the two variables? In a negative relationship, one variable increases and one variable decreases. So these scatter plots show a negative relationship. If you notice along the x-axis, the numbers are increasing, and the numbers start out high along the y-axis and fall. And so you get this falling kind of a line. And you can see that between the scatter plot on the left and the scatter plot on the right, the one on the right, the points are a little more closely linked to each other, and the ones on the left are a little more spread apart. So that's going to give you an indicator of some of the strength. The one on the right's a little stronger relationship than the one on the left, and we'll talk a little bit more about quantifying that in a minute. This slide shows another figure from your text. The scatter plot on the right shows a positive relationship. In the positive relationship, the values for one variable increase while the values for the other variable also increase. The correlation coefficient R quantifies the strength and direction of a relationship. The Pearson correlation coefficient, which is called R, is standardized, so it is not affected by the units of measure of the original variables. R ranges in values from -1 to +1. Values with an absolute value close to 0 indicate a weak relationship. Values with an absolute value close to 1 indicate a strong relationship. Positive values indicate a positive relationship, where as one variable increases, the other variable also increases. Negative values of R indicate a negative relationship. As one variable increases, the other variable decreases. There are loose guidelines for interpreting the strength of the correlation. And you'll notice between the Heavey text and the Navarro text, you got two different sets of guidelines. Heavey called anything under 0.3 weak, from 0.3 to 0.5 moderate, and above 0.5 strong. This really depends on domain knowledge. In nursing and behavioral science, that's probably a pretty sound guideline. A lot of behavioral science, if you have a correlation of 0.5, that's pretty strong. Navarro has a table where Navarro describes 0 to 0.2 as negligible. Sorry, my screen just cut out. Okay, there it goes. 0.2 to 0.4 is weak, 0.4 to 0.7 is moderate, and 0.7 to 0.9 strong, and 0.9 to 1 is very strong. For general correlations, this is probably a little better of a scale, so I'd probably lean towards Navarro unless you're in a specific domain where you know that it's following behavioral science guidelines. Pearson R is only valid for linear relationships. So these scatter plots, this is from the Navarro text, all have the exact same Pearson R value of 0.816. So only the first one in the top left corner is probably a linear relationship. The next one on the top right corner, obviously there's a curvilinear relationship there, and this correlation wouldn't be really appropriate for that. And then the two on the bottom, you'll see there's outliers in a couple different directions. So you really want to look at these relationships with a scatter plot before you go interpreting your correlation coefficients to kind of see if you can identify any problematic relationships between the variables. Spearman-Rowe is the non-parametric equivalent for Pearson R, and so when you violate some Pearson R assumptions, Spearman-Rowe would be a good option. And also for ordinal data, Sperman row is the appropriate correlation for that. Correlation matrix is used to examine multiple correlations at the same time. So you'll notice that the variable names down the left side, Dan sleep, baby sleep, Dan grump, and the examples in the Navarro text, you can look up what these mean. Match the variables in the column names, Dan sleep, baby sleep, Dan grump, and in the same order. Notice where a variable in the row intersects with itself in the column. The table just shows dashes, so these dashes here. Other statistical software will often put the correlation in, which would be 1, because any variable correlated with itself is going to have a perfect correlation, and the Pearson R value is going to be 1. The cells where variables intersect with themselves in the columns is called the diagonal. So that's the diagonal going from top to bottom, right to left, left to right, right to left, right to left, left to right. Sorry, left to right, top to bottom, left to right. The correlation matrix is symmetrical with itself around the diagonal. Other statistical software will actually take these numbers and fill them in the top. They're the exact same things, just symmetrically reflected across that diagonal. So this is what a good APA table for a correlation matrix would look like. And this is directly out of Jamovi. This table is showing p-values for the correlations, and significant correlations are indicated with asterisks. So these are options you can turn on or off in Jamovi. I like to see it because the p-value is always useful to know what's significant. And you'll notice that this convention, this is followed by most software. 1 asterisk is p significant at less than 0.05, 2 asterisks p less than 0.01, and 3 asterisks p less than 0.001. That's pretty common. To find a correlation of interest, locate one variable in the rows and the other variable in the columns, and look at the corresponding cell in the table to find the correlation between those two variables. So if we wanted to see the correlation between baby sleep and Dan sleep, we would find baby sleep in the rows, Dan sleep in the columns, and the intersecting cell is where we're going to find the correlation, 0.628. I'd probably call that a moderate strength, and it's a positive relationship. So as baby sleep increases, Dan sleep also increases. You can also see scatter plots for multiple variables in a scatter plot matrix. This is the scatter plot matrix from Jamovi, showing the scatter plot for the correlation shown in the previous slide. Notice the rows and columns are in the same order as shown in the correlation matrix above. The scatter plot matrix is also symmetrical around the diagonal. Other statistical programs often show the plots of variables with themselves down the diagonal and the symmetric plots in the top half of the matrix. Jamovi also allows you to show the correlation information directly in the scatter plot matrix to make things easier to read. So here's the same scatter plots, and then here's the correlation numbers. So this really is pretty easy to interpret. So if we're looking at Dan sleep and baby sleep, right there's the scatter plot, and if we just reverse that, we see baby sleep and Dan sleep. We can see the correlation between those two. And with correlation matrices, it really doesn't matter which variable you put first, because you're going to get the same numbers. Check test assumptions before interpreting results. So correlations do have a normality assumption. You want the data approximately normally distributed. You should have 2 continuous variables. Your sample is randomly selected from the population. You know that from the study design. Variables have a linear relationship. You're going to see that in the scatter plot. Observations are independent. And we have a new assumption we haven't really heard of before called homoscedasticity. And the variance in one variable is approximately equal for values in the other variable. So we can talk a little bit about this homoscedasticity plot, this homoscedasticity assumption. This is a scatter plot that shows when homoscedasticity assumption is violated. Notice how the points around the line are very close, near x equals 0, but spread out near x equal 10. So down here, pretty close. Up here, they're farther above and below the line than they are down lower here. This assumption is similar to the homogeneity variance assumption we looked at for t-tests in ANOVA. In homogeneity variance, we looked at the variance for the groups defined by the categorical variable. Homoscedasticity is the continuous variable version of this assumption. The problem caused when this assumption is violated is the p-values are inaccurate. The solution is to use robust methods, but we're not really going into those in this course. So this is, again, something you can identify by the scatter plot, and you just want to evaluate for this assumption when you're doing your testing, and note it if you see an issue with it. Be transparent. The effect size for a Pearson R is called R squared. That's called the coefficient of determination. And Navarro doesn't really go over this, but R on its own is considered an effect size. I've seen it used as an effect size for other tests, and I've also seen other effect sizes converted to R when they're doing some things using effect sizes. And all you do is take the value of R and square it, and it's interpreted as the percent of variance shared by the two variables. It may also be described as the percent of variance in one variable that can be explained by the other variable. So if you have a Pearson R of 0.5 and you square that, you're going to have an R squared, a coefficient of determination of 0.25, and you would say the two variables share 25% of their variance, or 25% of the variance in one variable can be explained by the other variable. We're going to go through the computer assignment and look at the steps for conducting a null hypothesis significance test for a Pearson correlation. So I wanted to make a note for you guys. Ignore the Hebe lecture from time index 2 minutes and 10 seconds to 2 minutes and 30 seconds. Hebe is talking about a chi-square. Never, never, never call a chi-square a correlation test. Hebe gives an example of selecting a test when you have a nominal variable and a continuous variable. And then Hebe says the best test used would be a chi-square because they say the lowest level of measurement should drive this test selection. And Hebe is partially correct here. So we've talked about other options. This is directly from our which statistical test table that we've been building. And when we have one categorical variable, which is nominal, and one continuous variable, which is interval or ratio, we've looked at the independent t-test, where the independent variable is categorical with two groups, and the dependent variable is continuous. And if you have three or more groups, then we've looked at the one-way ANOVA. So I honestly am not quite sure what Hebe had in mind when she said what she did, but I would not recommend, I would not make that same recommendation. So I have never in any other textbook or course heard a chi-square called a correlation test. Do not copy that language. So I don't think that that was a great explanation for that. Okay, that's all I had for this lecture, and we will talk to you guys later. And my screen cut out, so I've got to figure out how to shut this off. Let's see here.